So, good afternoon, ladies and gentlemen. Welcome to the last Monsoon seminar for 2022. And our speaker today is André Bahr from the University of Heidelberg in Germany. And we're dealing with a slightly different monsoon than usual today, where he's going to talk to us about circulation, ocean circulation, precipitation in tropical South America. André did his PhD at the University of Bremen, and he also studied geology in Heidelberg. After graduating, he worked for the University of Frankfurt, and since 2014, he's been on the faculty at the University of Heidelberg. So without further ado, I will turn it over to him. If you have questions, please put them in the chat and I'll call on you at the end. Thank you very much. André, if you want to share your screen, that would be great. Thank you.
So thank you very much, Peter. So I hope everybody can see my presentation now. So welcome to my talk, and thank you for inviting me to this very nice series of related to monsoonal research. So as Peter said, the topic today is focused on the South American monsoonal system. So maybe not the most studied or the most evolved system in the series. So I will try to give some new information about this issue. So by studying monsoonal system, of course, I mean, in this series, I don't have to convince anybody that it's important to study monsoons. But why the South American monsoon? Now, one thing is really important, that we have a big ecosystem hotspot there, for example, or namely the Amazon basin, which is in the heart of the monsoonal system. So it's important to understand how, for example, climate change in the past might have varied and impacted the ecosystem there. But it's also inhabited by millions of people, and the monsoonal system is very important for their well-being and from a social economic point of view. And of course, it's important for us as climate scientists or paleoclimatologists like I am to help understanding how future climate evolution, global warming, CO2 emissions will impact the monsoonal systems. And with regard to the South American monsoon, if you just look on this cartoon on this map here, it's not a model output, it's just instrumental data showing the reaction of precipitation to forcing by CO2, just based on instrumental data until now. And you see that, for example, here the eastern parts of Brazil, eastern South America, is reddish shading, indicating that you have a substantial loss of precipitation relative to an increase of CO2, while other parts of South America, especially here the subtropical parts, are mostly impacted by, or probably impacted by, a higher precipitation, or maybe also coming as flash floods. While this instrumental data might suggest a certain certainty, so to say, about our future climate change in the South American realm, computer models are not at all coherent regarding the future evolution of especially precipitation and moisture availability. There's a huge uncertainty between models, and also between models and proxy data. So what I want to do, and what is my major motivation for studying the monsoonal system, is to use the paleo data to have insights about the mechanisms governing precipitation across tropical and subtropical South America, and to help kind of understanding the system with regard to projections in the future evolution. And so to give you an outline of my talk, so first I will do an introduction about the most important elements of the South American monsoonal systems. And then I will present 3 case studies where especially focus on the oceanic impact on the South American monsoonal system on different time scales. I will first have a look at the orbital scale variations. That's research from Alicia, who was a PhD student in my group, and who will also give a talk in this series in January. So I'm really looking forward to Alicia's data about spatial variability on the monsoon that she will present in January then. And a second case study, I will dive in more into the millennial scale variability. This is work that is mostly related to the PhD research done by Karl Meyer, and also in the group here in Heidelberg. And last but not least, I will look at the short-term variability, like centennial, submillennial scale variability that we had in the Holocene, and what we can learn from this variability regarding also future climate change. And I will then wrap everything up with take-home messages and outlook, what we might have to expect future climate change. So first, let's start with the monsoonal system, the South American monsoonal system. Because South America is mostly on the southern hemisphere, so just to orient you, here is the equator, 0 degrees. So most of us in the southern hemisphere, the major phase of the monsoon, the typical South American monsoon, is occurring during austral summer, so December, January, February. Only the northernmost parts and Mesoamerica then are affected by northern hemisphere, by boreal summer as a major phase of the monsoon. The South American monsoonal system is a relatively new recognized system. That's maybe also one reason why it has not been studied that extensively compared to, for example, the Indian or the Asian monsoon, because it does not include a kind of inversion of the wind system, which is typically related, for example, to the Asian monsoon. But South America, tropical, subtropical South America, has a very, very pronounced seasonal variation in precipitation, which makes it, in our present understanding, a typical monsoon system as well. And one of the decisive features of this monsoonal system is, of course, the intertropical convergence zone, the ITCZ, which migrates southwards towards austral summer and reaches northern Brazil, more or less, but not much further south, and brings precipitation to this area here. Then we have a second very important convection system. That's a so-called South Atlantic convergence zone, so to speak, the sister of the ITCZ, or the brother, I don't know. So it's very important if you look here, starting from the Amazon basin, going down to the more eastern parts of Brazil into the subtropical, tropical Atlantic here. So that's the SACZ. These both features are probably one of the most important parts of the monsoonal systems, affecting large parts of Brazil especially. Then as another important factor, we have the South American low-level jet, which transports moisture brought in by the ITCZ along the Andes mountain chain towards the south, and then depending on the atmospheric situation, towards the subtropical parts of the continent. So that's also very important for distributing moisture, and is an integral part of the monsoonal system. And so these are the most prominent parts, the most obvious parts, which will pop up every now and then in my presentation. Because I will also especially focus on the interaction of ocean circulation and terrestrial continental climate. It's important also to look at the major oceanographic features. There we have, on one hand, the North Brazil current, which transports the warm, salty water from the tropics towards the north into the Caribbean, that eventually then gets fed into the Gulf Stream system. And then as a divergent current, the Brazil current going further south. So it's important to notice that we have one southward and one northward flowing surface current along the coast of South America. So that's basically the most important aspect of these precipitation or the system of the South American Monsoon, which, just to remember, is maturing in during austral summer. So let's start with the first case study. So we were looking at the orbital variations of the Monsoon system, and here I repeat partly something that has been already presented by Cristiano Chesi in his very nice talk earlier this year in February. And later on, I was also go back to more recent stuff that has been presented by Matthias Wü in November this year. So partly I will repeat what both of these colleagues said in their very nice presentations, and I encourage everybody to look also into these presentations on YouTube to have more details on stuff that I'm saying in this regard. So if you look at the orbital scale variations in the of the South American monsoon, we recognize that there's a very strong insolation pacing, which is not really surprising, given that monsoon systems are typically forced by summer insolation. The stronger the insolation, the stronger is the monsoon. Not very surprising. We see this in this record here, which has been published by Alicia. It's from a sediment core of the Rio Doce here in the southern parts of eastern Brazil, relatively close to the main center of the SECZ. So it's a record typically representing the monsoonal variations. This record goes back around 320,000 years, so far the longest continuous record of monsoonal variability. And we just used very simply the classical titanium-calcium ratio, with high titanium indicating strong input of the Rio Doce River, and low titanium-calcium ratios low input, so weak monsoon activity. And that's this blue record here on the here, as you can see. And as you can also see, this record really nicely follows a precession cycle. If you see here, this reddish curve is a precession filter. And if you compare it with the precession forcing, the orbital precession as the forcing of low latitude insolation, you see that's as expected, really nicely mirror basically of insolation. And as I said, it's a southern hemisphere monsoon system, so precipitation is obviously strongest during austral summer. And from this point of view, it's expected that we have an anti-correlation, for example, to monsoon systems in the northern hemisphere, and that's really true. If you look here at the Sambao Hulu Dongye cave stack from China, we see that, of course, we have this precession phasing during the past 320,000 years, and it's brought in the way that we have wet conditions facing down, and in the case of Sambao Hulu Dongye, and we have wet conditions facing upward in the case of the Rio Doce outflow in our core. And it's obvious that both records are very nicely anti-correlated, as you would expect from this situation in different hemispheres. So anyway, so that's very nice. That's very consistent. We were really surprised how nice this was following the insolation. Anyway, there's one particular interval that is a bit odd, and that's stage 6, marine isotope stage 6. You can see it here, the entire stage 6 marked, and especially this interval at the beginning and towards the middle of stage 6. And you see that there's not much variability going on in the titanium calcium record. The entire record stays on a relatively high level. So to say, it's always having been really relatively wet. And it's somehow missing a beat in precession. You see that precession here. If you look at the forcing, I hope that you can see my mouse. There's one precession beat, which is quite strong, and that's somehow missed, almost missed. It's very weak. And we were wondering why it's the case. Also, because we do not see this relatively this missing beat, for example, in the Chinese cave stacks? Is there anything particular that is happening, for example, in the South Atlantic during this part or this interval? And indeed, Alicia found that there's something strange happening. It's not only in Alicia's record, but we know it also from other records. And that's that we see a pooling of warm water happening, especially during this interval. And this pooling of water happens apparently in the tropical South Atlantic. And that's obvious, or that's visible from this curve here. That's from the same curve where I showed the titanium-calcium ratio. That's magnesium-calcium-based paleo temperatures from the sea surface from the same core, from the same sample. So we don't have any stratigraphic mismatches here. And as you can see, there's a lot of wiggle going on. We don't see a lot of precession or glacial interglacial variability, which is a bit strange. But what we see is that during stage 6, we have a continuous increase in temperatures, going from 25 to 28 degrees, which is quite substantial considering that we are here in the tropical Atlantic. And that's also mirrored by a core that is a bit further south here, GL 1090, which shows also a slight increase of temperatures towards the end of stage 6. So apparently there's something going on in the South Atlantic indicating higher temperatures here towards the end of stage 6. That's not so much visible in other parts of the tropical Atlantic. For example, in the Caribbean Sea, we don't have this kind of pooling of warm water. There's cooling before stage 6 at termination 2. And if you look at the equatorial Atlantic, there's also no warming going on. So there's something which is happening, particularly in the South Atlantic. And if we consider that temperature gradients are an important part in determining the position, for example, of wind system and the strength of wind systems, we were asking ourselves, is there any imprint or any effect these kind of pooling of warm water during stage 6 might have had, for example, on the trade wind system or other wind systems during this time. For this reason, Alicia computed different gradients to have a look what this means in terms of heat transfer and heat differences between hemisphere and within hemispheres. So I will guide you to this bit complex graph. So on these green line you see here, the interhemispheric gradient. That's the difference between the sea surface temperatures we measured here at our side of the Rio Doce River compared to North Atlantic side 1313 and the mid latitudes at 41 degrees north. And you would expect if you have a strong heat transfer to the north, like today, that we had a relatively weak gradient. And if you have a slow heat transfer from the south to the north, you should have a high gradient because this you would always sit in the tropical warm pool more or less, but 1313 might be influenced by cold, by subpolar waters, or at least cold waters coming from the north. And so sluggish heat transfer to the north then would indicate that we have indicated by a high gradient. And that's the case during stage 6. So it's if you look at the plot, it's plotted up the way up that we have a high gradient between both sides. And that's very unique to stage 6, that we have here a strong increase in the gradient reaching almost a maximum here, and then flickering about during the late stage 6. But it's indicating that we have a weak heat transfer and a strong interhemispheric SST gradient. What is also unique during this time, that we have also a strong intrahemispheric gradient. So for this, we compared our side of the Rio Doce to sea surface temperatures here in the at 45 degrees south in the Southern Ocean, which is a side a bit towards oriented towards the east. So we have north-south, but also east-west gradient incorporated here. And you recognize that we have a very strong gradient between both sides during stage 6. So this curve is also oriented upwards if you have a strong gradient. And that's really pronounced during stage 6, strong gradient and persistent strong gradient. And the idea is what kind of effect might this have on the precipitation, that this gradient, especially between this side and this side, would indicate that we have a strong meridional gradient within the southern hemisphere, which might have fostered the trade wind intensity, because trade winds are, of course, forced also by gradients in temperature, like every wind system, basically. And this can also be deducted from the titanium calcium record if we just remove the dominant precession signal. So, of course, insolation is dominating everything, but if we remove this aspect, then we end up with a persistent high titanium calcium record here, which is nicely following the pattern of the intrahemispheric gradient here, if you look closely. Maybe not so much during stage 4, that's a bit odd, but otherwise the shape of both curves, the interhemispheric gradient as well as the precession-free titanium calcium, indicates that we had a kind of influence by the gradient on the precipitation in eastern Brazil. And so that's one part of the mechanism that might have acted here. And the question is also what might have driven this kind of strong gradient. And one reason, one villain, so to speak, might be the CO2 content, because in numerical models or also observational data, it suggested that high atmospheric CO2 contents are reducing the intrahemispheric gradient. But during stage 6, you have a pronounced interval of very low CO2 content. Please note that this curve is flipped. So here we have a low content of CO2, and here we have during stage 5E a very high content of CO2. So that's been flipped just to show the similarity to the other curves. So in this case, this means we have a low PCO2 in the atmosphere, hence a high interhemispheric gradient, which would go very nicely in line with the Proxy data. And then the CO2 content as maybe a cause for this high gradient might then indirectly influence the monsoonal precipitation in eastern Brazil. So that's a way where maybe even CO2 forcing might have imprinted indirectly long-term variations in the monsoonal precipitation in Brazil, although I have to stress that the main forcing comes from insolation. So this graph here shows very briefly what we have what we have shown so far. So the typical interglacials, for example, stage 5, is that we have a frontal system located here, the subtropical to polar fronts, and and that we have moderate trade winds. If we have a look at stage 6, we have probably an expansion of Arctic sea ice cover and a northward shift of the frontal systems in the South Atlantic. So we have an induced strong gradient within the southern hemisphere, a strong SST gradient, which reinforces strong trade winds. And these trade winds then bring moisture towards the coast of Brazil. So that's probably a kind of exception in stage 6, and it would be interesting to see if stage 6 is also anomalous in other monsoonal systems, or if this kind of unique to the southern hemisphere Atlantic monsoonal system, like maybe the South African monsoon. So, okay. Yeah. So that's orbital timescale variations I've talked about. Now, let's have a look in the Mendelian scale variability. So that's a kind of classical textbook example how ocean circulation changes impact monsoonal systems. There's been a lot of papers published about, and in a brief way, it's that we have a very the weakening of the global overturning circulation during the high stadials, which causes a pooling of warm water in the southern hemisphere, much stronger than we would have during the stage 6 issue that I've just discussed. And these warm temperatures in the South Atlantic would change the atmospheric system in a way that we have, for example, moist conditions in the monsoonal system. And there was one kind of famous paper, for example, published in 2004 by Wang et al., who showed that during each seismic event, we have a growth of speleothemes and travertines in eastern Brazil. It's this location here, which is kind of odd because today this area is semi-arid. There's not enough precipitation to grow speleothemes or travertines. So this was presented then as an indication that we had wet phases during the Heinrich stadials, reinforced by the oceanic imprint, the change in the global heat distribution during Heinrich stadials. Based on this paper, there have been a lot of publications, and it's still not quite settled yet how, for example, the spatial distribution of wet and maybe also dry phases during Heinrich stadials was back in time. So that's an issue I want to talk a bit about. Just to give you an idea about the magnitude of change we have here in the ocean heat transport, there's one core that Karl Mayer just have published last year. Here from southeastern Brazil, relatively close to the coast, was in the Brazil current. And he measured magnesium calcium temperatures based on surface dwelling foraminifera. And the results are here presented in this red curve. And you see a big peak, which exactly coincides with Heinrich Stadium 1 or even Heinrich Event 1, around 16 years before present. And this peak has a magnitude reaching from 24 up to almost 30 degrees. Maybe there's some kind of salinity effect, but we have certainly a magnitude here of 4 or 5 degrees centigrade within the tropics. That is huge, and that is really significant. So we see that there's a lot of pooling of warm water, which is really, really kind of anomalous during this part in time. What we also see, if we have a look in a record from the northern hemisphere, that's here where the star is located. Sorry, that's in the Tobago Basin. There we have also sea surface temperatures, which show exactly at the same point where we have this anomalous warming here offshore southeastern Brazil, a cooling also of a magnitude of maybe 4 degrees, which more or less coincides and indicates that we have a weak transport of warm waters by the North Brazil current. It's probably retroflected here into the tropical ocean again. So that's a cooling here, but a warming here. So we have a huge interhemispheric temperature difference, which should have impacted the monsoonal system by a lot. And that's kind of obvious if you also look at proxy records and modeling. So that's a publication by Maria Campos that Cristiano Cesi already presented in detail in his presentation back in February. So I wouldn't go into detail here, but just to give you the two most important outcomes of this study is that first, of course, we have moist conditions in eastern Brazil, for example, like we saw from the growth of the speleothemes and the travertines. But we also have other parts in the continent that haven't seen any big changes. For example, here around the southeastern tip of Brazil, or we have parts in the northern part of the continent which have received more like a dry period during Heinrich events because southward shift of the ICZ which brings not more, of course, like more an arid climate to this area. So this is, for example, the Caraco Basin record or Orinoco catchment, which shows aridity or dry conditions during Heinrich events, in contrast to the large parts of the monsoonal system, which gets wetter. But as I said, it's not the entire part that's getting wetter. We have a complex situation here, and complex not only in terms of spatial distribution. We see here, for example, that there's a lot of moisture during also summer here, concentrated in eastern Brazil. But we have also a seasonal imprint that, for example, Austro-winter precipitation, which is usually not part of the monsoon or not part of the monsoon per se, is concentrated here in central Amazonia. So it's not that easy as it was thought first, and then turned out by giving more and more proxy records that we had a pretty complex situation during Heinrich stadiums, both in space and both in time. And just to add on this complexity, Carl was also studying the high resolution variability of the monsoon during the peak of the Heinrich event. We had these very huge SSTs, and how this relates, for example, to the subtropical parts of South America. And there we found a very interesting dipole pattern. So just to show again the SST record that I already shown here from his core in southeastern Brazil. That's the red curve here with the huge peak in SSTs during the central Heinrich Stadium 1. And exactly during this peak, there's happening nothing in his in the same record, showing that we do not have a big variations here in Southeast America. So this is bluest curve here. You see a bit wiggles, but there's basically nothing happening related to Heinrich Stadium 1. And this is nice because it reinforces what has been seen in the model, that this region is relatively neutral. So we can say that there has been the SEC apparently above this area, but there had not been a change in the intensity of the SEC or any substantial movement. So it's been more like it has been during the LGM or later during the early Holocene. But that's different if we go to the southern subtropical parts of South America, to the La Plata Basin. That's the uppermost record here. That's also based on XRF scanning, like his like Karl Mayer's record, interpreted like the iron potassium ratio interpreted, showing wet conditions facing upwards. And there you see exactly where we have this huge peak in SSTs in Karl's record, that we have there a peak also and precipitation in the La Plata Basin. So there seems to be kind of a neutral position here and a lot of precipitation going on in the subtropical parts, especially La Plata Basin. And how to reconcile this? And there's Carl developed the idea that we had a kind of dipole between the SEC and the South American low-level jet. Just remember here, that's a feature going along the Andes towards the south, towards the subtropics. And just to briefly explain this scheme, it shows this kind of dipole we have. So that's again here the South American coast. Here's Brazil. Here was Carl's core, which showed essentially nothing during Heinrich stadiums. And here's the La Plata outflow, which shows a lot of precipitation. And this kind of neutral dipole with this dipole pattern between warm temperatures here offshore eastern Brazil with not much changing, and a cooling here in the subtropical parts of the Atlantic is a situation you find also in present-day climatology, and that's often related to Rossby waves going through the high and mid-latitudes of the southern hemisphere, which influence the position and the strength of the low-level jet especially. So that's the bluish arrow here shows the moisture transport, and in some instances, moisture gets directed from the low-level jet straight to the east towards, for example, here the position where we have southeastern Brazil. But during these situations where we have warm water here and cool water here, we have a southward directed low-level jet, which brings a lot of moisture, a lot of strong precipitation events towards the La Plata basin. So that would explain, based on modern climatology, why we have this kind of dipole also between these both areas, and somehow fits also to what we know about the SST distribution in the South Atlantic during Heinrich stages. So that's adding in new perspective on the already quite complex situation during Heinrich stages. But it's really nice that we see it in the proxy data, but I think it's also one way to, or should be also one incentive for modeling community, for example, to look if we can also reproduce this pattern by modeling, if we force it, for example, by the SST distribution that we see based on proxy data. And last but not least, in my last part of the talk, I would like to focus on the late Middle Holocene, like the last 5,000 years. And based on what we know from the orbital as well as the millennial scale variability, we have seen that there's a lot of imprint of oceanic forcing on the precipitation in tropical, subtropical South America. So our question was also, can we somehow reconcile oceanic variations with precipitation variability and the monsoonal system? And there I also would like to go back to Matthias Wühl's presentation back in November. We had talked in detail about Little Ice Age, medieval warm periods, a really great talk. I wouldn't go into this detail here, but just to also put a new perspective on these kind of issues. Do we see impact of oceanic changes? Do we see an impact of high latitude climate variability on the tropical precipitation variability in South America? And what we did is obtaining an XRF scanning record of the discharge of a relatively small river here in the eastern parts of Brazil. We have a fairly high sedimentation rate here, so we can really go into details here, at least related to centennial submillennial scale variability. And the record that I will show here is these, which I discussed here, is a blue record here from this core, and which is basically showing the terrestrial input from this region. This is today a relatively arid region for most of the parts, except the very coastal regions, which are covered by an Atlantic rainforest. But otherwise, the inland, the major part of the catchment of this small river is more or less semi-arid. What we use here is the potassium-aluminum ratio, interpreted as a proxy for weathering intensity. So if you have a lot of chemical weathering, you are mobilizing potassium, so you get an aluminum-rich soil. So we would expect, if we have moist conditions, that we had a low potassium-aluminum ratio in our sediments, and vice versa, a high potassium-aluminum ratio in our core if we have relatively dry conditions. So that's also where we have these arrows here showing, helping you to get the orientation. So facing upward, we have wet conditions in our catchment. We also added to the XRF scanning elemental data, hydrogen isotopes measured on leaf wax on the same core material, of course, in less resolution, but at least you can see that the trend of the signal is quite similar. So we are quite sure that we have a solid record here of moisture variability in this region here. And what you see first is that we had a long-term trend towards drier conditions over the last 5,000 years. And This trend fits nicely with insolation, but exactly opposite to what one might expect. So this is insolation here in the uppermost part of the record, of the graph here. It's plotted upside down for correlation purposes. So we have an increase in austral summer insolation during the mid to late Holocene. So typical monsoonal system, you would expect an increase in moisture variability, an increase in monsoonal strength with higher insolation. That's what we saw looking at the long-term record of the Rio Doce River, which followed so nicely the insolation pacing. However, here we have the opposite. It's getting drier, although we have a high insolation, and that's related to the development of the nor'easter low. So that's a very important part also of the monsoonal system, that we had subsidence here over northeast Brazil, bringing dry air to this area. So during the high phase of the monsoon, this is actually quite dry here. And it seems to be that this nor'easter low has been enlarged, especially over the mid to late Holocene, so that our little river here get more and more into the influence of the nor'easter low over the long term. However, if we look at the small scale variability that is preserved in the XRF scanning record, you see that there's a lot of fluctuations. It's not just one straight line, but we see, for example, huge change in moisture availability at around 2,000 years ago, where we had wet conditions and then suddenly, more or less suddenly, dry conditions. So this is a big shift in the system. And we see also some kind of prominent variability during the medieval climate anomaly, as well as the little ice age. Although the age model is not as precise as we have, for example, in the speleothemes, we definitely see that we had some centennial scale variations also during this period. So we're wondering, where does this come from, this variability? And there, it's interesting to note that we had a really striking anti-phasing to the speleotheme from Botovera, which is located here in the northern subtropics of the continent, which is an influence of the low-level jet and perhaps the southernmost parts of the SACZ. So we have apparently a kind of dipole between our little river here and Botovera Cave here. That's valid for the long-term trend. As you see here, this red curve, this Botovera, red is again facing upwards. So we have kind of anti-correlation if we compare it to our record. But also the small-scale variability is mostly anti-correlated, especially here during at around 2,000 years ago, where we had the trend towards dry conditions, and here we have a jump towards wet conditions. And you're wondering what might have influenced this kind of dipole. And based on present-day climate situation, it's that we in fact have a kind of dipole between SECZ and low-level jet. So that's modulated by North Atlantic climate, especially. That's the Atlantic multi-decadal oscillation, the AMO, which is apparently influencing the strength of especially the low-level jet. So if we have a negative AMO, we have a strong low-level jet. And at the same time, we had probably a weakening of the South Atlantic convergence zone. So this would explain that we have this kind of dipole, because if we have a weak SACZ, then we should expect that we had less precipitation here. But at the same time, we have a strong low-level jet, so I have a lot of precipitation here in Botovera. So this might be an indication that we have this kind of high northern latitude forcing implemented also in the Holocene record, which is also kind of nicely agreeing with other proxy records from South America. And last but not least, it's interesting to note that we had also a striking similarity to proxies of AMOC strengths and Gulf Stream strengths, so indicating heat transport on a global scale. these are the both records here in the lower part of the figure. This AMOC strength here based on from the Garda drift in the South and the North Atlantic and Gulf Stream strengths here, and both records have the same trend as well as same high resolution high frequency pattern, especially at 2000 years ago, where we have our distinct shift in the monsoonal system here, and both records from our record as well as from Butuvera, and distinct change in AMOC strength as well as Gulf Stream strength. So this would reinforce the idea that South American precipitation reacts highly sensitive to Northern Hemisphere climate, and this might have been modulated by global ocean circulation strengths. And this, of course, might be of concern also for future climate evolution related to global warming, if you believe projections of a weakening of the AMOC that we had might have a similar kind of pattern of drying here and more moisture, and maybe flash floods here in the part where Butuvera is situated, so southwestern Brazil and southwestern South America. So this might be a mirror of what we might expect in the future. So just to present the take-home messages, the most important aspects of my talk. So first is, if you look at the orbital time scales, we see that insolation forcing is, of course, like the pacing of everything, but we have also an overprint of oceanic forcing, especially during this mysterious anomalous stage 6, which is still puzzling us a bit. Why stage 6? Second, we have an immediate impact of AMOC changes during the Heidi stadials and also Danske-Oeschger cycles probably, but it's spatially complex, and also one needs to look at the seasonality there. And we see that even small-scale changes in AMOC and North Atlantic climate variability might have influenced South American precipitation both spatially and in the strengths during the Holocene, and that's something we might expect also for the future climate change. And then last but not least, the question: what is CO2 doing on the monsoonal system? So based on the proxy data, it seems to be that's not the direct forcing, but an indirect forcing, for example, by modulating the SST gradients within the southern hemisphere or between the northern and southern hemisphere, so that we had an indirect CO2 imprint. So that's basically the take-home messages from my talk, and thank you very much for listening to this talk, and I'm happy to answer any questions.
Thank you very much, Andre. And so if anybody would like to ask a question, you can just request to do that. And Cristiano has a question. Do you want to unmute yourself?
Yes. Can you hear me?
Yes.
Yep.
Good. So thank you very much, André, for this very nice overview. Very good to see you and to hear this talk. You know, after the work you have done and others as well, what would you say now, you know, looking back to what has been done, that it would be the open questions on past behavior of the South American monsoon?
Yeah, thank you very much, Cristiano. Nice to see you. Yeah, it's a good question, because I think one of the big variables that is still unsolved is the CO2 forcing. So we saw that maybe it's not a direct imprint on the proxy data, but it appears that there's some kind of indirect modulation, for example, on the SST gradients, which then influence the monsoonal precipitation. It would be interesting and really necessary to quantify which kind of effect does it have. And I'm not a modeling person, but I'm not really sure how good the models capture this kind of feedback between CO2 and SST forcing and the impact on continental climate. So putting numbers on this issue, I think, would be really, really interesting. That's for me one of the big questions that's still out there. I think Alicia in her talk then in general will also talk about CO2 influence and other factors influencing this spatial impact on the monsoon. So I'm really curious what the state of the art is in her data.
And we have a question from Torsten. Torsten, do you want to ask your question? Or I can read it for you if you like.
Sure, I can. So I was looking, can you hear me?
Yeah.
Yes.
Okay, sorry. Oh, my camera. Oh. Well, looking at your explanation of the gradients in the southern hemisphere during stage 6, I was just wondering, you mentioned the sea ice expansion one slide later. Have you compared the gradient or the variations in the gradients with the sea ice expansion, so that there might be some imprint of the sea ice expansion on the gradients?
Yeah, that's the idea that Alicia had, that like sea ice extension during stage 6 might have reinforced this strong gradient that is basically based on the CO2, but then reinforced by sea ice gradient. But we are still lacking a good proxy data, as far as I know, or long proxy record, which we might use to really show that this sea ice extension is substantially larger during stage 6 compared, for example, stage 8 or stage 2. So that's something, at least I'm not aware of any record that really shows this increase. So that's kind of speculation, but I think we need some kind of feedback, and sea ice, in my point of view, is a good way to have these feedbacks on the wind systems, not just SSTs.
Can I ask another question, Peter?
Absolutely.
Looking at the Holocene stuff you showed, I am not really familiar with the area. Is there any impact of El Nino in this area as well, or is it just by the, well, North Atlantic, AMOC, Gulf Stream, and so on? Yeah,
that's also very tough and really good question, Enzo. And in the case of the Eastern Brazilian part that we are investigating, that's ENSO neutral. So that's a good point, that we can somehow remove ENSO from the equation if you look at our records. So based at least on modern climate data. It's not so easy for the subtropical parts. There, I believe we have an ENSO influence. So that's really kind of part of the issue, that we have so many forcings acting to remove it from the equation. But based on modern climate, my understanding is that the Atlantic forcing is a bit overwhelming, what we know from El Nino, but we cannot put El Nino aside, especially for the southwestern subtropical parts of Brazil.
I was just asking because we had the same thing in Tibet and the monsoon story, and we found similarities to ENSO, which has exactly the same decrease in precipitation and increase in El Nino around 2000. So this really sharp shift, which you all had already had in your data as well. So that's why I was asking about that. Thanks
that's really interesting. Yeah.
Are there any other questions? Andre, there was one thing I didn't really understand. So you were highlighting the anomalous character of the MIS6, but I didn't really understand why MIS6 was so strange. I mean, as opposed to other glacial times.
Yes, basically, maybe I can share my screen again. So if you look at the long-term variability of the monsoon, we see that we have this nice insolation forcing here. And during stage 6, this correlation to insolation forcing does not really break down completely, but is somehow muted.
Right.
So we would expect much drier condition during stage 6.
Mhm.
And this was one thing that we started puzzling. So we were thinking about sea level influence, for example, on the titanium calcium ratio. So if you have a low sea level, then you would have automatically more input of terrestrial material, but the record does not show any sea level imprint. And we see the same pattern, for example, if you look at seawater salinity reconstructions based on combined delta 18O magnesium calcium measurements on the forams there. So it's really kind of missing this precession beat that we would have expected.
Right.
Yeah, that's the reason why we're thinking that's a bit anomalous. And what I didn't detail here in my talk is that colleagues in Frankfurt were looking at the clay mineral composition in this record during stage 5 and stage 6, and they found that stage 6 is also anomalous in terms of clay mineral composition, that we have a lot of stuff from the coastal area, which is usually not so much transported to the core side. And they were arguing that we have a lot of coastal precipitation, which is usually related to trade winds and precipitation brought by trade winds. So, and that's kind of unique to stage 6. So this is basically the reason why we said that stage 6 is a bit outstanding here.
Yeah, very interesting. Are there any other questions for the speaker? If not, perhaps you will join me either using your reaction button or just clapping using your hands to thank him for his presentation. And I would like to wish you all a very happy holidays, Merry Christmas, Happy New Year. We will be back with more seminars in January, but next week is AGU, and then we're going to have a break until early January. But please come back. I'll be sending out emails about all that. In the meantime, stay safe, stay healthy, and have a good rest of your year. Thank you very much.
And thank you, everybody. See you.